Welcome back everybody to this video on functions. So in our last lecture we talked about relations, which is this really abstract seeming idea, which of course it is. It's the sort of thing that you would spend a lot of time on in say an abstract algebra course. In our case where we're interested in doing analysis, what we really need relations for is the language to talk about functions. Right? So obviously functions are critically important as we learn this, what I often describe analysis as is the theory behind calculus. So, what's a function? Well, our definition of a function is the following. So suppose we have two sets, A and B, then a function from the set A to the set B is a non-empty relation. Oh, there's where relations come in because a function is defined to be a kind of relation. That's why we had to spend so much time talking about those. Well, not just any old relation, but it's a relation with these properties, right? That whenever you have an ordered pair x comma y contained in f, and then another ordered pair x comma z contained in f, then y has to equal to z. Oh my goodness, what in the world is that? So in your high school experience and then through college, you've probably encountered functions where you've written things like f parentheses x, right? So f of x, and you've talked a lot about functions maybe more as a rule. So here we're defining a function as a relation. What in the world is going on here? Well, that's a great question. And so this is a way to be very precise. As we've said before, whenever we're writing proofs or explanations, we want to be very, very precise with what we're saying. Here's a way to be very, very precise about what we mean when we talk about a function, rather than just say it takes an input and produces an output. Okay, so what in the world is this thing on the screen doing to to produce an output the way we think about a function, right? Well, in this case, the ordered pair x comma y, right, is really telling us everything we need to know about f of x and its input and its output. The idea is the first element, that x, of course, right, is you can imagine that being the input to the function, and the second element, y or z, depending on which part of the line there at the bottom I'm looking at, is the output of the function. Right? So what this relation is telling us is x is related to y, and in that last line, x is also related to z. And in order for this to be a function, the only way that could possibly work is if y and z were both the same number. Okay. Okay. So again, we're probably much more used to writing f of x equals y, right? Instead of saying x comma y is an element of this function, which is really weird sounding when you first say it. Because remember, we're thinking of a function as a relation, which was a subset of the Cartesian product, A cross B. Okay, so what if we translated our definition into language maybe we're more familiar with? What this really says is that if f of x equals y and f of x equals z, the only way that could happen is if y and z were really the same thing. One way that you'll hear this said in like high school algebra is when you put an x into a function, there can only be one possible output. Right? In this case, this is exactly what it's saying. If you thought you had two outputs, a y and a z, then no, they both actually end up having to be the same thing. Okay, when you look at something like this, it's reasonable to ask yourself, why have you done this, right? Why can't we just go back to drawing little pictures of a machine where an x comes in this way and comes out at the other end as an f of x, right? Well, again, we're trying to be very precise. Why do we want to be precise this way? Well, one reason is because of graphs, right? So if you think about what a graph is, so we usually graph something by drawing Cartesian coordinates like this. Well, what is that? That's R2, right? That's R cross R that I've drawn a picture of there. All these possible ordered pairs of real number, comma, real number. Okay? And when we graph things, what we're really doing is coloring in the function. The cool thing about defining a function this way is that the function really is its graph. It really is all the ordered pairs, right, that belong to the function if we think about it as a relation, Or if you think about it the way we typically do in high school algebra, we draw in the function, right? And every point on that curve that we're drawing the graph there, every point on that graph looks like x comma f of x. That's the deal, right? The first coordinate is the x coordinate. The second coordinate is the y coordinate, which is the value of the function when we plug x into the function. That's usually the way we say that. Right? So this rule about having every x value correspond to only one output, right, or only one second coordinate in the ordered pair is the typical vertical line test. Right? If we look at everything that could be matched up with an x, so look at all the possible y coordinates that could match up with that x, there can be only one. It's like Highlander, right? There can be only one f of x given a particular x. Okay, so we need a little bit more language. We said this was a function f from a to b, right? This set A we call the domain of f. Now the picture I just drew, this looks like, it's supposed to look like x squared, more or less. So the domain here is all of r. This is a function which takes any real number and produces some other real number. Well, what other real numbers can I get? Well, that's of course the range. So we can write this now in our fancy set notation. The range of this function is the set of all y's, which would be contained in b, right? That's the second part of this, because a is a function, f is a function from a to b. And so there's all the y's so that there exists an x back in a, so that f of x equals y. That's what the range is. It's all of the y's so for which there exists an x so that f of x equals y. If you think about this on the graph, that's all the y coordinates so that you can go back and find an x so that that y coordinate is f of x for that particular x that we found. Okay, so the way we would normally try to find the domain here is you start drawing some, say, horizontal lines. If we look at this horizontal line, that goes through one particular y coordinate. So is that particular y coordinate, where I've drawn the horizontal line through there, is that an element of the range? Well, yes, because there are, in fact, two different x's, so that y equals f of x for those two different x's, those two different points I have there. On the other hand, if I drew a line a little bit below that, right, something down around like -4 or -5 or something, way below this, then for that y, there's no graph there, right? That line does not intersect the graph. That means for that value of y, there isn't an x that I could plug into the function and get that y out, right? So that y value would not be a part of the range. Now, sometimes it might be a little confusing because we talk about the range, and we also have this a and b that we've drawn in here, right? At the very beginning, we said a function f from a to b. That a was always the domain, and then this b is just left hanging out there. Right? Sometimes people call that a codomain or give it other names, but the idea is it makes it simpler when we talk about a function to not have to require that the b be exactly the range. So what we'll usually have is a function that maps r to r. That's how we will write it. F maps r to r. But r might not necessarily be the range. Right? In fact, in this example, r is not the range. Right? It looks like the range is like from like, I don't know, -3 or something up to infinity. But it's definitely not all real numbers as the range. Okay, well, you may have seen that horizontal line I just drew there, right, as a test for telling whether something is one to one or whether something is onto, and these sorts of words from back in high school algebra. So our definition of one to one and onto will be this: so a function is onto, or a better word, a nice French sounding word, is surjective if that b is actually equal to the range of f. In other words, when I say I have a function f from a to b, right, if that b actually is the entire range. So for every little b inside the set b, there is a little a back in the domain, so that f of little a is equal to little b. One way of looking at that from the graph is that means that every y value gets hit. So if I drew a horizontal line, then that horizontal line would go through um, every horizontal line I could draw like that would hit the graph. Um, Also, an extremely important definition that's closely related is a function could be one to one or, nice French word, injective, right? If whenever you have f of a1 equal to f of a2, that implies that a1 equals a2. Okay, so graphically, this means if I draw a horizontal line, I look at the y coordinates, that it only hits the graph once. Okay, just like the vertical line test, the horizontal line test says you draw a horizontal line, if it only hits the graph once, then it's one to one. Um, what this means in the way we've written it, and this is much nicer in the way we've written it, because it gives us kind of well, a handle on how we might prove something is one to one. How would you prove something is one to one? Oh, look, I'm proving an implication. Well, you spent a very long time talking about how you write proofs and how you prove an implication. So you could do a direct proof or an indirect proof or however you are happy doing this, but we're proving that if f of a1 equals f of a2, then a1 had to equal a2. Now, we might have a function which is both one to one and onto, or another way of saying that is both surjective and injective. That's really cool when that happens. And when it does, we call a function like that bijective, or a one to one correspondence, because for every element in the domain that matches up with exactly one element in the range. And so that's really cool. We will see one to one correspondences again in a future lecture when we talk about cardinality of sets. Okay, a couple of more definitions. So suppose that we have a function that maps A to B. So A is the domain, okay, maps A into B. And C is some subset inside of our domain. Then the image of C is, oh goodness, what's this? This looks really weird, right? I'm writing f of C and I claim that this makes sense when really what I'm doing is at this point I'm horribly abusing notation. And everybody does this and we will because it's so convenient, but this is kind of a terrible abuse of notation. So usually when we write function parentheses then something then another parentheses, that something is a number that we're plugging into the function, like we might write f parentheses 2 parentheses, right? That's a y number that we get out when we plug 2 into the function for the x. Here I've written f parentheses c parentheses, where c is some subset of the domain. It looks like I'm plugging a whole set into the function. And I mean, the function would choke on a whole set, right? What's it supposed to do here? And it looks like on the right hand side of that equal sign that I'm getting a set out. I mean, this is weird. Well, I mean, so maybe that's one way to think about it, is that I'm plugging a whole set in and I get a whole set out. It's like we're doing the hokey pokey. And we put your whole C in, you get your whole F of C out. Okay, so what's really going on here is we're abusing notation by using F of capital C to denote a set, and it will call that the image of C. And what it is, it's the subset of B that consists of f of little c, where little c is an element of capital C. So you can sort of imagine this as plugging the entire set C into the function and all the possible outputs that we get from that. We call that the image. We could kind of go the other way too, although this is even more of an abuse of notation. Suppose that we had a subset of B. Okay, we'll call that D because I've already used C and alphabetical order seems to make sense here. So if I have a subset D in B, then I can look at the pre-image, or sometimes what people call it the pullback of D. And that's, well, okay, this is even more of an abuse of notation because now I've suddenly written F with a little -1 subscript. Okay, what in the world does that mean? So whenever you teach high school algebra and you introduce inverse functions for the first time, which is not what this is, by the way, right? You introduce inverse functions for the first time, that little -1 just confuses students, terribly, because it looks like F with a -1 as the exponent. And so they all think that means 1 over f. Right? But of course it's not. An inverse function is not the same as 1 over the function at all. And this is not even an inverse function. This is a pre-image. So this is like taking d, and it almost looks like I've stuck it into the inverse function. We haven't talked about inverse functions, and f might not have an inverse. So what does this even mean? Well, again, it's a horrible abuse of notation, but it makes sense, when you write out the definition and look at it as a set. So D is some subset over in B. Its pre-image, which we write so that it looks like f with the minus 1 of D, is the set of all the a's back in the domain, so that when you plug a into the function, you get something in D. Okay, so again, this is not that complicated of an idea, but you're looking at something which, notice I haven't said something in the range; it's something in B. So it's entirely possible that if the range of my function was not all of the set B, in other words, if my function is not onto, then the pre-image might of some subset in B, might be the empty set. There might not be anything that mapped onto that set. For example, in that example we saw a few minutes ago, where I drew in a graph of a parabola, and we said if you have numbers which were large negative numbers, right? Does that make sense? Large negative numbers, negative numbers that all the way down on the y-axis. If you look at the pre-image of a set of those, right, there were no x's that mapped onto those y's. So the pre-image might be the empty set even. Okay, so this definitely needs some work, right? We need some examples, and we need to do some things with this. So here's one thing that's fairly easy to prove. So suppose that you have a function from a to b, and again c is some subset of a, then c is contained in the pre-image of the image of c. Wow, that looks confusing. Okay, so let's unpack what that says. Right. So this almost looks like I'm taking C, which is not what I'm doing, but it looks like I'm taking C, plugging it into F, then plugging that into F inverse. And so shouldn't that take me back where I started? Why this contained in? Why not equal to? Well, that's a good question. The answer is it's not true. Uh, but you know, remember that the F with the little minus 1 does not mean inverse of function for F. It just means pre-image of this set. So C is a set. When I write F of C, that's also a set. That's the image, right? And I'm taking that set and finding its pre-image. And C should be contained in that pre-image. And the proof is not very difficult at all, right? This is a typical sort of proof using sets, right? I want to show that one set is contained in another set, so I'm going to do a direct proof by taking some element, little c, which is contained in capital C. So I'm going to take an element on the left-hand side and show that it has to be contained in the right-hand side of this C contained in blah blah blah. The pre-image under F of the image of C under F. Ooh, that took a long time to say. Okay, so I picked my little c. Now the whole deal with the image of a set is that the image of C, which we called F parentheses C parentheses, is the set of all F of little c's, where the little c's came from C. So clearly, F of C would be an element of the image F of C. Okay. Okay. Now, what was the pre-image of a set? Well, those were all the elements back in the domain that mapped into that set. So again, this is a little bit of just notation chasing things around here. But if I start with an element, little c, in the domain, then f of c, obviously that's in the range, and it's in the image, f of c. The pre-image was everything that got mapped onto f of c. Well, of course, c got mapped onto f of c because that's what f does. Right? Other things might have got mapped onto f of c also. For example, if my function had been x squared, right, and I look at, suppose my c had been 2, right, what happens to 2? Well, f comes along, finds the 2, it says, you know what, you need to be squared. So f of 2 becomes 2 squared, which is 4. Okay? But then you say, okay, well, what gets mapped on to 4? Right? If you look at the graph, a horizontal line hits the parabola twice, right? That's because there's two things that get mapped onto 4 by x squared. Not just 2, but also negative 2. Okay? So the pre-image would have not just 2 in it, but also negative 2 in it. And of course, that's exactly why, right, the containment doesn't work the other way. Right? So if we wanted to try to prove that these two things were equal to each other, which it kind of looks like maybe they ought to be, that the f and the f with the minus 1 exponent looking thing, which of course really isn't, this is symbol for pre-image, remember, that those cancel somehow and that should be equal to, not just see as a subset of, we need to prove that the containment goes the other way, right? This typical proof with sets. And it doesn't work that way. And here's a counter example. Again, remember, we spent a long time talking about how proofs and counter examples and all that works. So we would have all that language now to use. So here's our counter example. Look at x squared. Right? So take a whole set, like all the negative numbers, including 0. Okay? What would its image be? Well, if I take any negative number and square it, I get a positive number. And if they're in 0, I get 0 squared is still 0. So the image of all those negative numbers would be all the positive numbers, and including 0, because 0 squared would be 0. So the interval from 0 out to infinity. So stick in all the negative numbers, and I get all the positive numbers. Okay? But what's the inverse image of all those positive numbers? In other words, what's the pre-image of the set of positive numbers? That's r, because every positive number, right? Like again, think about 4. Right? It has two numbers that got mapped onto 4 by x squared, 2 and negative 2. Right? So this is how, of course, you run into trouble trying to find inverses and stuff. The problem we're running into here that makes this work is that f is not one to one. So when we look at the pre-image of a set, we get more than we started with. Okay? So the pre-image of the positive numbers, including 0, is all of r. Okay, so I've said the word inverse functions a few times and hinted that this was coming. If we had a function which was bijective, so remember that means one to one and on to, then you can define an inverse function. And so doing this with relations and the way we've talked about things with our sets of ordered pairs as the function, right? We think about if we have an ordered pair x comma y being an element of the relation which defines the function f, then all we do is we just switch the x's and y's around. Or if we do this in the notation maybe we're much more used to seeing, if f of x equals y, right, then f inverse of y should be x. And because it's one to one, then there is only one x that goes with a given y and vice versa. Right? Okay. Now, if this is not bijective, you don't have an inverse. And so, again, the one-to-oneness was obvious. Why do I need the onto-ness? Well, I need it to be onto because I need to be able to define my inverse function as a map from B back to A. And if B is going to be the domain of F inverse, then it really needs to be the entire range. Otherwise, I'd have stuff in B that didn't come from something in A, and I wouldn't know where to map it. You can also define the identity function on a set. This is really cool. So the identity function, there's lots of ways to write this. Some people write it with a capital 1. I'm going to use a little lowercase I with a subscript A. And so this function just takes an element of A and spits it right back out. So the identity function gives you identically what you plugged into it. Right? It's sort of like when you multiply something by 1, it doesn't change it. Right? The identity function just takes something from A, it maps A back to A. It's one to one and on to, obviously, because you plug in an A and you get back the same A. Okay? Now, the cool thing about inverse functions is they're going to work like this. If you take f and then you compose it with f inverse, then you get the identity function. Right? So again, if f were a function from say a to b, then f would map you from a to b. F inverse would take you back from b to a, and assuming everything is all one to one and onto, and this inverse function really exists and it's really an inverse function, then you get back what you started. Right? And it works the other way too. If you start with b, you take something in b and plug it into f inverse, it goes back to a. Then we hit it with f, and it goes back to b. So we get just the identity function on the set b again. And of course, if you had some function which went from b to a, right, and if you compose it with f one way and you get the identity function on a, and the other way you get the identity function on b, the obvious sort of way here, then g had to have been the inverse function for f. Okay? Suppose that we had two bijections. So a function f that went from a to b and a function g that went from b to c. Then when you do the composition, so first we do f, then we do g, that'll be bijective too. Right? And if you say, oh, what's bijective? It should have an inverse function. It does. So if you take g composed with f, inverse, right, that's exactly f inverse composed with g inverse. And now you might ask yourself, why did the order switch, right? Because I wrote g composed with f, and now I got f inverse composed with g inverse. It looks like almost like you distributed the -1, but then switched the order around. How did that happen? Well, you have to think about how the domain and ranges fit together. So think about the function g composed with f, right? So in other words, first f and then g. Okay. So if I do first f and then g, then that will go from a to b, then from b to c, as far as sets go, right? I take something from a, it maps it to b, take something from b, and then that maps it to c. And so when I do its inverse, it ought to start with something in C and then go back to B and then go back to A. So that's why the inverses have to be written this way, where I do G inverse first, which takes something in C, sends it back to B. Then F inverse, which takes something from B and takes me all the way back to A. Okay, so this needs a proof, right? So first let's prove that this composition really is bijective. So I'll take an element little c inside the set big C. Since G was onto, there's a little b that maps to it, right? That was the definition of onto. So G of this little b is equal to our little c. But of course, F was onto, so there's an A back in the set A, so that F of A maps to that B. And now, of course, when you look at the composition, A will get mapped by F to B, and that gets mapped by G to C. So, since my C was arbitrary, this composition has to be onto. Okay? So, for one-to-one, it's a really similar sort of idea. We just go through the proof here, right? So, what does it mean to be onto? Well, it means that whenever you plug an A1 into the function and an A2 into the function, and you get the same thing out, the A1 and the A2 had to be the same. Okay, so let's take an A1 and plug it into F and then G, and then take an A2 and plug that into F and then G, and suppose that those are equal to each other. Then, if we're going to prove this is one-to-one, which is part of proving that it's bijective, we have to prove that that the F of that the A1 and the A2 are equal. Okay, but G is one-to-one. So G of F of A1, we're assuming, equals G of F of A2. So I've plugged two things into G, right? They were equal to each other, so the original things I'm plugging in had to be equal to each other. In other words, F of A1 had to be equal to F of A2. And F is one-to-one. So the definition of one-to-one for F says that the A1 and the A2 have to be equal to each other. That means that the composition is one-to-one. So those two things together tells us that the composition was bijective. Right? And then showing that the inverse is what I said it was is really easy. It's just sort of a matter of symbol pushing. So suppose I take F inverse composed with G inverse and compose that with G composed with F. Then you start untangling all the things that happen. the G composed with G inverse in the middle becomes the identity map on B. So you can just ignore that because it just takes an element and doesn't change it. Then I end up with F composed with F inverse there, and that's just the identity map on A. And the same thing happens when we do it in the other order. So F inverse composed with G inverse really had to be the inverse of G composed with F.